working on those algebra problems that we gave you, the pink sheet yesterday? Okay? If you didn't pick up a pink sheet yesterday, you need to. You'll be tested. It'll go on the summative, I believe, on the algebra concept. The pink worksheet from yesterday is still over there. Did I what? Is that the right one? Okay. Okay, you guys. This one? Oh, I don't know. We'll give you time. Okay, you guys, let's look at the schedule. I have it up on my whiteboard. So we have 3 days on this. So today, Wednesday, Thursday, working on these problems. And then you have a quiz on Friday. Quiz will take you the whole time. If you don't do the problems, you're going to die on the quiz. Well, you won't like it. You guys have to do the work. That's true. Right. Might be, I don't know. Let's get started so we get through this. Okay. Okay, guys. Possibly. Okay. Casey. 3 more weeks before break. Okay. These are related rates. They're called related rates for a reason. It has been on the exam on free response many times. Has not been on free response, Riley and Brian, for a while now. So Mrs. Hersman and I think that we have a pretty good chance of having at least part of a related rate question on your exam this year. But they're easy to prepare for. Okay, Matt? Noah? They're easy to prepare for if you do what I tell you to do. Now, on the back of your handout, for those of you who like to have step-by-step instructions, there it is. I'll just talk about it as we do it. Well, first thing is I want to read the problem. Okay, Jack? We're going to read the problem. A small balloon is released at a point 150 feet away from an observer who's on level ground. We keep it simple. We don't deal with air resistance, any of those things. This is an application of derivatives. That's all it is. Why would we do derivatives? We need to have a use for it. Here's one of the uses. And it says the balloon goes straight up at a rate of 8 feet per second. How fast is the distance from the balloon to the observer increasing when the balloon is 50 feet high? So yes, you have to read and interpret. So as I read this, I have a diagram already set for you, and the key points here look like 150 feet, 8 feet per second. How fast is the distance from the balloon to the observer increasing when the balloon's 50 feet high? I at least like to do that myself. Often you get points for this find, give, and when. Not sure exactly what piece they'll give you the point on, but some of it they will. It just depends on the scored rubric for that year. So I drew my picture, and then it says to label your diagram with things that are constant in time. Well, the only thing that's constant in time is the distance from the observer to where the balloon is released. How far is that? Okay, you got to make sure you get the numbers in the right place. Now, on the units, I'm not going to worry about units. However, on the exam, they may ask for units. They may ask you to interpret the units. So you might need a little practice with that, and there may be some in the problems. Explain what that means. Explain what the unit means. Like this is 8 feet per second. It's positive because the balloon is going what? Up. If it were negative, what would the balloon be doing? Going down. Right, could be that. Okay, a lot of you want to label the 50 feet. You can't do that because what's happening? The balloon is starting here and it's rising. What's changing? The hypotenuse is changing, and what about this side up here? Yeah, whatever you want to call it. So I'm going to undo that. So this is changing in time. What would you like to call that height? Okay, we'll use h in the next one. It doesn't matter. Now, I don't want to put in 50 feet here, Alexi, because then that's a constant. And if that's a constant, then the hypotenuse is a constant. And if I take the derivative of constants, I get what? 0. They're changing. So this is talking about derivatives. It's a rate of change. So I know this is changing. And what do you want to call this length? It's also changing. Oh, I don't like X. Z. Okay. Call it what you like, but if you want to match your notes, you want to call it the same thing. Okay. The balloon goes straight up at a rate of 8 feet per second. They tell me that. That's given. And it says, find the distance from the balloon. How fast is this distance from the balloon to the observer increasing when the balloon is 50 feet high? So 50 feet high. Well, let's put some variables with that. What is that one? When the balloon is 50 feet high. I could freeze this. So y equals 50. Okay. What's the 8 feet per second? It's the change in your position divided by your change in your time. That's your velocity in which direction? Velocity is a rate of change. So this is what? The change in what? Ever look at your diagram. Which one is it? It's the change in the y as t changes. That's a derivative. I want the instantaneous, not the average. And what is it I want to find? How fast is the distance? I want to find out how fast that's changing. What is that? The change in what? Z as what changes? Time changes. You can have derivatives with respect to anything you want. This makes sense. We're going to do it with respect to time. These are changing. How do you talk about how y changes? That's the derivative. Because I want it at an instant. It's at 50 feet. It will look like this. But if I take a derivative now, what's the derivative going to be equal to? 0. So that's the problem. If you look at the steps, the last thing you do is put the 50 feet in. I'm going to leave that picture because I'm going to need it in a second. Now here's the secret to related rates. At least to me, that's the secret. When you do the find and the given, those are the ones you want to relate. There's a relationship between y and z. And what is that relationship? Look at the picture. You know it. Whose theorem? You could do angles, but I don't have anything about angles here. I want to relate z and y, and the thing I think of about is Pythagoras' theorem. So 150 squared plus y squared equals z squared. Don't solve for y or z. That's too hard. We'll do it implicitly. Is that okay? You know the relationship here. And some of you are saying, well, that's not the relationship with the velocities. Well, it is if I do what? How do I find the velocity? Take the derivative, because that's what a derivative is. It's an operator. So we're going to take the derivative with respect to time, because that's what I want. I want to dy dt into dz dt. Because if I plug in 50 for the y, what's the derivative of the left side going to be? 0. It's not 0. Think of this as a snapshot. I take my camera, and when the balloon is 50 feet high, I will take the picture, and I can find that side then. But this is changing, isn't it? It's always changing. Okay. What's the derivative of 150 squared? 0. You know how many times I see 2 times 150? A lot. That's 0. What's the derivative of y squared? Times There you go. If you understood implicit differentiation, this should be clear because I'm taking with respect to time. So it's the derivative of y squared, which is 2y, times the derivative of the inside. Chain rule. Now it's 2z. That's the derivative of z squared with respect to z. Then I have to do the derivative of z with respect to t. If I wanted this to be a z and a z, that would be fine. Then that would be 1. That doesn't do me any good, though. And then before I try to solve for anything I'm looking for, I like to simplify it. What can I do to both sides to make that easier? Yeah, divide everything by 2. Now, I have everything I need, almost, equals z times dz dt. Let's put in what we know, and then we will figure out what we need to know. Okay, it says I want to find dz dt, so I want to find this one. And it says that dy dt is 8. What did I what? Because I divided by 2. You could keep it in there. I could. I'm just going to put numbers in right away. We will here now. Because it's changing. You can't put things that change into your equation that's changing. You have to do that after you've done the derivative. So what's y? Y is 50 feet. So this is 50 feet times, and what's dy dt? 8 equals z times dz dt. So I just have to divide by z, but I need to know what z is. Now, you do know what z is. And some of you will do just Pythagorean theorem, and that's fine. 50 squared plus 150 squared equals z squared. And so you could say z is equal to the square root of that mess. And I'll just show you, just because I think it's interesting, I'm going to make a similar triangle to that one. I'm going to make it 1/50th of the size of that one. So on my new triangle, which is not drawn to scale, I'm going to make this 1/50th. So I'm going to divide by 50, divide by 50, and really basically divide by 50 on my green one. So what's this side going to be? These are similar triangles. This is 3. So that this side I can do now in my head. Square root of 10. Does that make sense? 1 squared plus 3 squared. This Pythagorean theorem. Now to get back here, I had to divide by 50. So to get back, this will be 50 times the square root of 10. Just kind of split, that's all. You could leave it this way. Nothing wrong with that on the free response. And so I'm going to put in 50 times 8 equals 50 times the square root of 10. dz dt. Then what are we going to do? Divide by 50 square root of 10. Divide by 50 square root of 10. What happens to the 50s? You can leave it, by the way. It's perfectly okay. What happens to 50s? So I get 8 over the square root of 10. I have a better feel for how big that is. Because what's the square root of 10 approximately? Give me a whole number. It's about 3, right? It's about 8/3. You don't have to. You can go to decimals if you want. Because I want to find how fast this is changing, and that's a derivative. What is a derivative? It's a ratio of two changes. So the slope of a line is a derivative. Delta y over delta x is how does y change if x changes? That's all it is. If you have a curve, if here's your x's, there's your delta x. How does your y change? Find the slope there. That tells you the y change. And we'll do more. All this chapter 4 is going to be nothing but applications. Is it? dz dt? Not necessarily. It's kind of weird. It seems like it would be, but no. Because you know what? It's going up pretty fast with that distance because the distance is increasing. he's going to increase slower. When you see the next problem, when you put water into this cone, how fast is the height changing when you're there versus here? Which is going faster? The bottom one. So I think it's similar to that when you talk about the length of that hypotenuse changing. Okay, now I want to get all that out of there. I could not find, when I tried to build this, some sort of faucet with water going in. I couldn't do it. Now, water's pouring into a conical cistern. You guys know what a cistern is? It's a well. And on my farm, where I brought up my child and my family, we had a rectangular prism for a cistern, which is the way it should be. It's the way they usually build them. They're not going to build them in the shape of a cone. It's kind of weird. I don't know, but the AP people want you to be able to do the geometry here. And why is that? No, well, because we also had an oil tank for our oil. We heated the house with oil. And in the middle of winter, you don't want to run out of oil. Now, if they put the tank in the ground like this, we could have easily measured the height and calculated the volume. That would have been easy, but they didn't do it that way. They put it in like this. Yes, it wasn't very nice. So we had to do calculus so that when we measured down here, we had to actually figure out what volume was left. And you didn't want to run out of oil at 40 degrees below zero, because then you have to restart the whole furnace. Not Waconia. Well, now the guy who bought it from me, he's got electric in there, but I wouldn't have put electric in. It's expensive. But anyway, so that's what we used to have to do. So we had to do calculus, actually, to figure out how much volume we had. There were no gauges on there. So we had a tape to the inside of the kitchen cupboard door. It was a little printout of what the volume was given the height. I know, it's weird. It is. So I'm going to get this out of the way. You can see the water is going into my well. Not well, but it's going in there. I really don't know. It was as good as I could get. I haven't, but this is old. This is like 5 years old, so maybe there's something better out there. So water's pouring in at the rate of 8 cubic feet per minute. That should tell you something. 8 cubic feet per minute. The height of the cistern is 12 feet. That's not going to change. The radius of the opening is 6 feet. Not going to change. How fast is the water level rising when the water is 4 feet deep? So let's label the things we know are constant. Okay, so my radius was 6 feet. That's 6 feet. And my height was 12 feet. I think that's okay. And the water is going in, and it's going in at the rate of 8 cubic feet per minute. I'm going to put the units in just to help me out, if nothing else. What's cubic feet? What's that a measure of? Volume. So this is volume, and this is minutes is time, so that's what? dV dt. Does that make sense? That's the change in the volume as time changes. And it says how fast is the water level rising. So that when I put the water in here, let's just take a snapshot. The water level might be right there. They want to know how fast this length is changing. Now I need a relationship with volume of a cone. Do you guys know what that formula is? Not 4/3, as you think of sphere. 1/3 pi r squared times h. No, they will give that to you. I'll give that to you. Yes, they'll give it to you. Although the sphere one they did not give 1 year. I don't know why. But that was the European one. Okay. They have 2 tests. They have one in Europe and they have one here. Last year they did not do that. Last year they did it very differently than that. Well, I did this year. This last year I graded the international one because they all took the same test that you guys took. I can't tell what country they're from, but I can tell that they're not from here because their handwriting. Like their X's, like we do X's this way, they do their X's this way. So it's very different. The handwriting is very different. But I'll also give you the good news. We did just as well, if not better. It's yeah, it's in English, but I still have to read it. Their writing is actually very nice. They're probably in an English school of some sort. Okay, back to the drawing. So looking at this formula that I'm going to use, what would you like to call that length? No, look at the formula. H. Yeah. No, that's at the snapshot. It's H is changing. What else is changing? The volume's changing, and the third thing that's changing, the radius is changing. So let's call that R. They're both changing. So if I were to take the derivative of this volume equation, unfortunately, both R and H are changing, so I'd have to use the products rule. And they have done that, by the way. Well, we're going to get rid of R or H. I'll show you that in a second. So I want to know how fast is the water level rising, so I want to find what? How fast the water level is rising, the change in what? H. They could have asked how fast is the radius changing, but they didn't. They asked how fast is the water level rising. When, what's 4 feet? Okay. Remember, I told you when you do these problems, you want to relate these variables, V and H. So I want to keep V and I want to keep H. I don't want the R. Because it's changing, and if I'd have to use the product rule, and then I'd have to know how fast R is changing. And I can, it's just way harder to do that. So we are going to eliminate the R squared as soon as we can. And I'm going to do some geometry to do that. So there's my picture, and I'm going to outline it. First I have this triangle, and then I have a little triangle inside there. So I can pull them out if I want. There's the little one. These are what kind of triangles? Similar. This is 12. This is 6. This is R. This is H. Now, you guys, you can do it this way. I don't like it. You can go R's to H. Remember, the triangles are similar. The sides are proportional. But I'm not going to do it that way because I want to get it right. And literally, the theorem is the ratio of the little triangle to the big triangle. So R is to 6 as H is to 12. And you can do the ratio within the triangle, set them equal, but you better make sure you don't accidentally flip one of them. If R is 3, what is H? 6. Okay? But R is changing. So multiply by 6. So R equals what? Oh, I'll do that. 1/2 of H, right? Or H over, no, 2. Divide. You get the right idea. So let's go ahead and put that into my volume formula. Now I know what this is, so I'm just going to write it down. Now 1/3 pi, those are constants. When I put in R squared, do I have to use parentheses? Yes. So it's H over 2. Now, if I take the derivative now, again, I have to use the product rule because H squared is changing and H is changing. So why don't I simplify that first? So it's pi in the numerator. What's the denominator going to be? I have a 3 and I have a 2 squared. 2 squared is what? 4. 4 times 3 is 12. Now, how many H's do you have here? I have 2 there, 1 more. It's a total of, does that make, pardon? I replaced R with H over 2, and I just multiplied that out. That's H times H times H, which is H cubed. What? Because what's 2 squared times 3? Remember, that's squared. It's 1/3 pi, H over 2, H over 2, H. Multiply those out. That's 12. I'm just simplifying. I haven't done anything. Doesn't matter. It's pi times H cubed. It's the same thing. These are all times. Okay. I haven't done any calculus, you guys. Calculus is the easy part. What do we have to do? You know you're going to take the derivative, right, Alexi? Okay, there it is. I want a dHdt and dVdt, so let's take the derivative of both sides. And this one bothers you too. Is pi over 12, is that a constant? Can I pull the operator inside that? Yes. Because you can always ignore the constant. It's there. You got to keep it there. But you can ignore it, at least for the time being. So I have dv dt equals, and it's pi over 12. And what's the derivative of h cubed? 3h squared times the derivative of the inside function, dh dt. And those of you who say, well, I have to use the product rule, okay. And it's plus h cubed times the derivative of pi over 12. Well, what is that derivative? 0, so why do it? We've done this a lot of times, and then I like to simplify before I go much further. dv dt, some of you don't. I like to do it. What about it? It's still there. Because it's plus then h cubed times the derivative of pi over 12. What is that? That's 0. Remember, you can always pull the derivative operator inside a constant times a function. So this is pi over 12. Oh, can I reduce that? What's 3/12? Pi over 4. What's h? H was 4. So that's 4 squared times the h dt. And what else do I know? I think I know dv dt, don't I? H is 4 feet. And dv dt is 8. That's why I do that. Then I have the numbers out of the problem, because I don't like word problems either. That makes you feel any better. But the more you do, the better you get. So 8 equals pi over 4 times 4 squared times dh dt. dH dt. And then what happens to the 4s? 1 goes and 1 stays. So I get 8 equals 4 pi times dH dt. What do you want to find? What's it say in your find statement? I can go back up. 8, because they gave it to me. You got to go back up here and look at your given conditions. You're given this. H is 4. You're given dV dt is 8. Just substitute it in. Yeah. I canceled the 3 and the 12. Just numbers. Because some people didn't like it when I ignored the pi over 12. They wanted me to use the product rule. I said, okay, I will, but that's gone. Now, you guys are having problems with the arithmetic and the algebra, not the calculus. Okay, Riley. Yes, you're given that. I did it down here. 8 equals pi over 4. I mean, you can put the numbers in right there. If you want to go 8 equals pi over 12 times 3 times 16 dH dt, it doesn't matter. It's the same thing. But that's just arithmetic. Yes, thank you. Divide by 4 pi. I don't care how you get there. All of you will get there in different ways. I like to simplify as I go, so things aren't so complicated. So it's 2 over pi equals dH dt. And it's positive, so the height's going up. Pardon? And they can. I'll give you plenty of problems. They're going to ask you to interpret what that means. Okay. Are we ready for the last one? It's a lot easier. This is probably the hardest one because you had to get this relationship right here. You had to get that relationship. Now, you guys, this part with the similar triangles, guess what? You'll see it on the exam. I looked at every multiple choice exam I can look at. I've either seen it on multiple choice or I've seen it on free response. You will see the similar triangle piece. More? What problems? That's why you need to do the homework. I know, that's why you're going to do the homework. Okay, ready for the next one? Turn the page if you're ready. You're going to need to know something. I'm going to let you guys do it. What's your question? Oh, are you okay? Okay, we have, this is a snowball? Oh, we have a soap bubble. Retains its spherical shape as it expands. How fast is the radius increasing when the radius is 2 inches if air is blown into it at a rate of 4 cubic inches per second? What formula do you think you have to know? Oh, okay. 4/3 pi r what? Not squared, because it's got to be cubic. Now, I think they might expect you to know that one. So I'm going to let you try it. And I'm going to walk around. Maybe we'll have time to start the homework together or not. You know I'm going to check to see if you even tried it last night. Your homework. Yeah. The assignment that's on the assignment sheet. You know that one?
Did we just get this?
Yes. Did you not get one today?
No, we just got it today.
Yep.
How did we do homework last night?
Didn't ask you to do homework last night. I'm talking about tomorrow. You know I'm going to check.
Oh.
Plus, you were supposed to do some algebra. Yeah. Perfect. I've broken it down as much as I can break it down. It just is what it is. Well, I'm going to come around and help you. I'm going to stop this.